Hi, welcome to this video. In this video, I'll be explaining to you how a parallel plate capacitor works, and of course, how does a dielectric in the middle of the parallel plate affect its strength. If you haven't watched my earlier video, do go back and watch the video about what is a capacitor, because that will tell you and teach you as to what actually a capacitor is, and then come back to this one to learn more about parallel plate. So get your notebooks out and let's get started. Okay, so a parallel plate capacitor is denoted by this, okay, two metal plates separated by a small distance d. The metal plates, one of them has a positive charge, another one of them has negative charge. Okay, so this is how a parallel plate capacitor works. So obviously a plate will have a finite area. Let's call that area A, and the charge is already written by us. We'll see how this works. Now this parallel plate can have in between different materials which are called dielectrics. So it can be air, it can be water, it can be other things. Okay, but for the first example, for the first case, we are just taking it as a vacuum. That means there is no material inside of it. Okay, we'll come to the effect of dielectric in a bit towards the end of this video. So how do we figure out? So I'm not talking about how a capacitor works in this video. For that, please watch the other video on our channel. This one is only about how a parallel plate capacitor is and how do we figure out the formulae for this. Now there are two very big assumptions that we are taking over here. What are these assumptions and why are they important? Two assumptions that are there are: one, the distance between plates is very small. That is, D is smaller than A square. D square, which is D square, is smaller than, very small than A, which is the area. Okay, I'll come to why it's important in a second. Second, the plates are huge. Okay, that means A is quite big. Both of these are very important. Why? Because for a parallel plate, okay, or for even a plane conductor, what happens is, at a plane conductor, towards the edges, the electric field fringes. The electric field fringes like this. Okay, for a finite plate capacitor, right? This is called the fringing of electric field. But obviously this is an edge case and increases the complexity of our situation. So to mitigate that, to remove it from our discussion at the moment, we have taken the second assumption that the plates are huge. When the plates are huge, we can assume to a certain accuracy, to a good accuracy actually, that the electric field within the capacitor, in between the capacitor, is parallel and straightforward this way. Okay, so this is a very important assumption, so that we know that our electric field is directly towards the other plate, to the second plate, and does not fringe. Okay, now the first assumption is important because of this, because of a small distance, I can say that my electric field is constant everywhere. My electric field is constant everywhere. Electric field for a plane conductor is equals to sigma upon 2 epsilon naught. This is what electric field for a plane conductor is, and to use this result I have to assume that the distance d is really small compared to the A, which is the area of the plates that we have. Okay, really important things, as we'll see how. Once we have the assumptions in place and once we understand why we've used the assumptions, now the important thing here is to understand why we've put the assumptions. Okay, the assumptions doesn't mean that we are jumping off things, it just means that we are trying to simplify the problem to get it to our level, right? As you go into as you go into university and maybe even PhD and whatnot, you will start removing these assumptions, and as you remove the assumptions, the complexity of the same thing gets magnified quite a bit. Okay, so that's where we put these assumptions to simplify things at the level of high school for us. Now let's talk about the electric field. You can see that this parallel plate system divides the whole plane into 3 segments. Let's call this one, let's call this second, and this is the third one. Third one is in the middle of the two. So for the first case, the electric field would be this way for the first plate, so this is E1, okay, and this way for the second plate E2, so this will be E1 plus E2, which is gonna be equal to sigma upon 2 epsilon naught, positive for the positive one but negative for the negative one because it is attracting the same, which is equals to 0. So the electric field over here is 0. By the same concept, just put in a different way, different place. Electric field in this area is also 0. Okay, now you should have asked, okay, you should have been able to question why am I taking these numbers and answers. Okay, so the question that should have popped in your mind would have been, hey sir, why are you taking sigma upon 2 epsilon naught from this plate also, from the second plate as well? Okay, because the distance over here is obviously much larger. The reason is that D is really small compared to the area A, coming back to the assumptions that we have taken, and because of that I can neglect this distance from the plane, okay, from the plate. Okay, and of course we do not see, like in the electric field of a plane conductor, we do not see any variable for the distance, and so we can take that as same. That's why I am able to come to this conclusion that on both the sides I have 0 electric field. Now coming to the third one, in the third one of course I will have the same thing, E1 plus E2, which will be equals to, here as well I will be adding them together, but as you can see that both the directions of the electric field are in the same direction, so I will simply add them together, giving me sigma upon epsilon naught as my result of electric field in between the capacitor. Very important result. Okay, once we have that, let's quickly find out the capacitance of this capacitor. Now capacitance, okay, for capacitance I need to first find the potential. Potential is essentially electric field into the distance d, which gives me sigma upon epsilon naught into d. Now in all of this I haven't told you what sigma is, so my apologies. Sigma is essentially charge, surface charge density. Okay, now what is surface charge density? Simply put, if my charge is spread across the entire surface, then I want to know that for a particular area